participants here. So, Bismillahir Rahmanir Rahim. So, in order to define the inlet, one is inlet and one is other is outlet. So basically, inlet is defined in a water gym. For if you want to fill your tank from a top level. So if you want to define a pipe in order to fill a water from a top level, then you have to give the level from the base, that how much feet it should be above the base in order to define the inlet of that pipe. So if you want to define that height, you should define not in the case of elevation. In the context of elevation, you have to give the, for example, if it is the total maximum level of 690 feet and the base level of 635 feet, then you should give somewhat below the maximum level of water, about 688. We should subtract from the 685, so it becomes the 23, I think. So you should give here the inlet level in feet is about the invert. It is the invert level, okay? It's about 23 feet. If you define that, so in basically it's a pipe. So this level is basically the invert level. So you define that level in a inlet pipe or inlet pipe. And mostly if you provide a valve and when it's completely full, then that valve does work like such like that it stops. Mostly the pump is pumping a water in order to fill the tank. So the valve works like that, that when the tank becomes full, then it stops here the flowing of water from a pump through from the rising main through the to the tank. So it is defined in such a way that, for example, let me show you here that it show you that the level inlet walls start to close. So the elevation where the valve or the inlet valve should start to closing, and the level inlet valve fully closes. So it works like that, that for example, if you want to close the valve, so and also minimize the transient effect as well, so you give head that give the value that, for example, 23 is the that level of pipe, and you want, for example, that if the level of water reaches up to the 20 feet 20 feet from the base, then the inlet valve should keep itself active and start closing. And when it reaches to the, for example, 25 feet, so it become fully closed. So it become fully closed in order to prevent the flow from a tank through this wall, and it is always draining at the outlet provided at the bottom in order to provide the water for a water supply system. And basically when the water reduces from the top level, from the maximum level, so it's again open, the wall become again open and start the allowing the water flowing through the pipe. So it's continually behaving like that in order to prevent and allow the flow through the pipe in a tank. So here, for example, if you can define the 20 feet wall start to close and 25 feet the maximum, and discharge coefficient is basically give you by the manufacturer, that from where you buy a wall. So on that wall, the specification, the discharge coefficient is provided basically for you. So you can here write, for example, I want to 0.05 cubic feet per second per And you can also be defined a different type of valve, glow, circular gate, butterfly, ball. I will explain you later, inshallah. You can also define a different parameter for a water quality analysis. Inshallah, we will do that when we start a water quality analysis. So now let me show you that I want to add a pipe here as well. Okay. For example, I want to define a pipe. Is there all of the 6 inches? For example, I want to define it is a you can directly edit the all of the size of pipe directly by global edit. For example, I want to give you the value of storage. And so if you are designing the water supply network, so you should know about the size available in the market. If you design for that type of size that is not available, then it is useless to use that pipe in a water supply. And based on that, you decide that it's a good system for designing a water supply system. You can also check the define a material for it, or you can also set the value for the Hazen-Williams coefficients for it. And mostly if you also want to provide a check valve that to prevent a backflow through the pipe, then you can also provide it in the for that for each pipe where it is viable. Minor loss coefficient for each pipe should also be provided. This basically is provided based on the check valve, and these are the properties we basically when we run the simulations to the properties or the calculations, the flow through each pipe, the velocity and loss gradient that are calculated at the after the simulation will be appear here. And if you want to design a length of pipe, so we didn't design a length of pipe, so we will design. For example, I want to design it by myself. Global edit, make it check. Okay, so for example, if you want to design, okay, so these are the different properties of the pipe. You can define a zone for where the pipes lies, the commercial area, the residential area. You can also define a diameter, the material, the Hazen-Williams coefficients. So Hayes user defined length, so I has become 2 because I want to give it by myself. Just I'm giving it the 200 feet pipe of length. You can also design the check valve is provided in the pipe, so we are not providing any check valve in a pipe. You can also provide a minor loss coefficient or other thing installation years, and it's a boundary condition basically defined in order to separate the model based on the pressure. So we will discuss that also. Or it is basically wave speed basically defined the when the water hammering effect occurs in a pipe, that how much the water flows at the wave speed. So these are basically the water quality for the parameters for the water.
was there slow.
So okay, so these are basically the water. You can also define a different parameters for the water quality as well. You can also control different perimeters. You can also define a different perimeters for the pipe, for the pump, for the tank, that at which time you want to close the pipe and how it will behave. So based on the if condition, I will show you how to use this dialog box, the controls for the pump, for the pipe, inshallah. So based on that, you can define the controls for each pipe and for each tank and pump as well. Similarly, for the junctions, you can define the zone, the emitter coefficient, and also the elevation for the junction. And this is the pressure. Mostly, we use the local pressure dependent demand. This is basically the pressure at the junction based on the demand. In this case, mostly the demand at the junction is constant, it is not changing, and based on the demand on the junction, the pressure changes. But when I make it true, So I will give the local function. For example, I will define a local function here that the it's basically the exponential function which defines that the how the pressures will change based on the demand on the junctions. So basically the demands are increasing or decreasing. So based on that, the percent of pressure increases or decreases. Here you define the power exponent, and this is a threshold pressure. For example, if at a junction the pressure increases for us from 60 psi or 70 psi, so it will make at that point the demand constant. So we will discuss that in a detail, inshallah. I'm just giving you a through a brief introduction to the WaterGem, defining a different element and how to model it in a WaterGem. So I will make it false. So you can also define a different water quality parameters for each junction as well. So here I just want to run a model. So therefore I will define pump. Okay, let me define it from here. It's a flex table. You can handle the different types of parameters for a pipe, for a junction, for a tank here from A very easily. So I will go to the its scale length. Then why let me use the okay, you can define by your own, or you can define it as scale. So it is already scaled, so it is calculated, it has calculated for us the length of each pipe. So let me check that what is the length of this pipe. So it is a scale length. So it has already calculated for us. You can already you can also defined by yourself by your own the length of a pipe and the elevation of a pipe at a junction as well. So for example, I want to give here the elevation. So we don't know about the elevation. I want to make it from here, from a junction table. You can sort it from here as ascending, whether descending. Do it by ascending. You can increase the column, you can add the column. So these are the different parameters related to the pipe, junctions, for the tank, pumps. So different type of parameters. If you want to check the parameters for each parameters in numbers, so then you can do that from here as well. Let's define for the junction 5 about let me take it 580 620 600 590. We designing elevation to a junction, we will do that automatically. Inshallah, I will show you that how to do using DM or a contours. In EPNet, when you start designing water supply networks, so for each node you have to go to the Google Earth, taking the coordinates of that node, and by checking the coordinates of that in the Google Earth, and after that you have to check what's the elevation at that node. So it's very difficult to going off and on through the different softwares and checking for each node that what's are the elevation of that node. It sometimes may occur that if you change the node or a junction and displaces from one point to another point, so you have again to go to the Google Earth and have to find the elevation of that point. So it's a very cumbersome to calculate the elevation for each node. Or but in a WaterGem you can do that in automatically by using the contours or the DEM. Similarly, you can also assign a demand to each node. So I will directly assign, for example, I will create demand. No, just not. You can demand by node, and you also initialize for all the nodes and create a demand from here. So basically, if you want to add a demand, you can go to the demand control center. You can also assign a demand as a unit demand control center. So for just for to save time and go some through analysis, so I will go through just for the demand control center. You can, I want to globally edit that and giving the 20, for example 15 gallon per minute. Okay, if you want, if you have values in other units, you can easily change the unit, giving a value in that unit and again change it to the gallon per minute. So it is very flexible in terms of this unit. You can also design the pattern. Basically, when we design a water supply network, so basically we designed for through the whole day. So for the whole day, at the night the demands decreases. At the 8 a.m. the demands increases. Similarly, at 12 a.m. the demand increases. So by these factor, we will provide a pattern for the throughout the whole day, and we will provide that pattern for to each node. And we may also create a different pattern for a commercial area, for a factory, for a mosque, for a masjid, and then we can design these patterns at at each junction in order to calculate and in order to fluctuate these demands at different times of a day for each junction. You can also demand these patterns for a weekly, for a monthly. So it's very flexible. You can do that. I will show you how to do it, inshallah. So just for this analysis, I'm keeping it fixed. So I have designed each and everything. I think I should validate the model. These have some problem. What's the problem? Okay, if there is some problem in a model, then you can check here that what are these problems, and you can then manage. Let me go to the tank. We have some enable some options, that variable area, then we should, and we didn't define that as well. I should make define at 50, and for example I'm installing it as a 222 years. Variable tank cross section contain non-increasing values, contain duplicate values, and the last depth ratio must be greater than or equal to. So we didn't define that the variable tank, so therefore it's giving me error. Tank with separate inlet must have at least two connected pipes. So basically one is the inlet pipe and other is the outlet pipe. So I will just use the one pipe, because here I'm not using a pump, so therefore I will use a only outlet pipe. So I will take from field separate email for false. I will make it false, and now it will edit the. So no problems were found. So by doing this, if you find an error in a model, you will have to check. You will have to check the user notifications, and based on these notification, you can correct your model. Just run the model. So from the summary, you can easily identify that what are the demand of a whole network. The flow demand is about 165, so which we have designed to each node. So we just design a 15 gallon per minute, and by multiplying with 11 you will get the 165 gallon per minute. So in order to check the annotation or the pressure at each nodes, you can also by clicking on that, and you can easily check the here for each node the hydraulic grade, the demand, the pressure psi. So the pressure at that point is about 33 psi, the pressure head. So all of these properties of each node or each pipe, the flow in each pipe, you can observe here. The flow through the pipe 150 gallon per minute. From here the in this pipe the flow will be about 165 gallon per minute, because the demand of whole system is 165 gallon per minute. And the pressure at that point will be about 40 psi. So at that point the 15 gallon per minute will be removed. So so this pipe, the demand will be moving about, the flow will be moving through this pipe will about of amount 150 gallon per minute. Similarly, for this demand, uh, for this node, the 15 gallon per minute of demand is extracted from the system, and based on that, the demand will be divided based on the demand on these type of nodes, and will be distributed in these pipes. So 70 is flowing from this pipe and 65 is flowing from this pipe. You can also annotate your junctions. For example, if you want to label and you want to annotate the pressure annotation. For example, I want to annotate it for the elevation, demand, fire flow general, the results, and I want to check the pressure at each node. So you can check the pressure at each node. So basically it's merging with the junctions. So you can edit by providing an offset to it. For example, I'm providing a 3 offset in x direction and 3 feet in the y direction, and you can also multiply the height multiplier in order to show in a high size in a magnify form. So you can easily observe the pipes. Let me of these junction labels and pipe labels in order to see it properly. So at these nodes you can observe the pressure at each node, and you can observe that the elevation difference of this node is very high, is about 480 feet, and while the elevation of the tank is about 650. So due to this elevation difference, the pressure at this node is very high. You can reduce the pressure at this node by providing a pressure reducing valve just by clicking here. For example, if you want to reduce the pressure at this junction and this junction, you can provide a pressure reducing valve. Just providing here, you can, it will basically, the pressure reducing valve is acting as a node, as a junction, so it will split the pipe into 2 pipes. So the science basically shows that the flow is flowing in the direction and reducing the pressure at the downward direction, at the downstream direction. So if how much you want to reduce, you will give the value here. For example, I want to reduce it to 60 psi. So this is a type of valve. You can design different type of valves. The diameter of valve you will define here it is as well. So I think it should be of 4 inches, because the pipe diameter is about 4 inches. And then run or validate them. First of all, validate the model. No problems were found. Now again run the model. Let me check the elevation should be of I want to, the elevation should be, what is the elevation here? 580. And what is the elevation for 80? 580 for 80, so it should be of 540. Let me run again. Let me reduce the size of this. Mm, so now it have reduces the pressure up to say 76 psi. Just like that, you can reduce the water pressure through it. For example, I want to reduce the minor losses to the of about 5. Use this again. Hmm, 40 psi. So it will reduce it up to 66 psi. So based on just the value giving to the PRV, pressure reducing valve, it will reduce the pressure at that point where you want to make the pressure less, or you want to satisfy the standard of Pakistan, or where are you are and where you are working. Other thing I want to discuss, okay, I want to show you that, for example, I want to add some alternatives. For example, do I want to do fire flow analysis at a junction, this junction. One thing I want to show you that, for example, if you want to annotate, or if you want to give a color coding to each node, you can do it as well. For example, for pressure, you can also you can also do that by just color coding to of each node. Calculate range, full range, minimum of 4 psi, maximum of 80 psi, and you can do calculate these range like that. The ranges of these, the ranging from 4 psi to 80 psi, and apply that. It will show you by color coding that these you can easily identify that the red zones are shown, the red color are showing that at these junctions the pressures are very high, and these junctions the pressures are very low. So by basically by color coding you can do that as well. uh, Before running the simulation, you can also be justified that you what type of fraction method you are using, whether you are using a Darcy-Weisbach equation, Hazen-Williams, Manning modify Hazen-Williams equation. Similarly, what type of analysis you are using for you are doing. For example, you are doing hydraulic in only flushing, fire flow, constituent H, constituent and tracing H. So these are the different types of analysis you can do that in a WaterGem. You can also do extended period simulation. We will do that inshallah in the subsequent lectures. But here, just for sake of introduction, I'm just giving an intro. So therefore, I'm using only a steady state analysis. It's just give you a snapshot. In a steady state analysis, basically the level of water do not drains or do not decreases in a water supply network, in a tank. It remains constant, while in extended period simulations the water level in a tank increasing and decreasing depending upon the water coming from the through the from the source to the tank through the pump, or the water going through the outlet pipe into the water supply network. So depending upon these type of condition. Similarly, you can choose your different algorithm for the simulation of a water design of water supply network. You can use the EpiNet algorithms. You can also use the WaterGem's algorithm. And some these are the different stuff we will discuss that about later. So you can also define the liquid kinematic viscosity and specific gravity and different type of stuff like that, the temperature of water at which area you are working, so you can define the temperature as well. how much trials you want to do for a simulations, and the conversion frequency and conversion check cutoff. The other different parameters are basically hydraulic simulations. These parameters basically for the iteration purposes, that when you start and for what trials you want to run a simulation and data from like that you can use that for that purposes. Okay, what I want to show you that, for example, I want to show you that I want to for example, design a fire demand disjunction. So I will go to the fire demand, I will create a new alternative, child alternative. I will click on that, and what's the design, let me check it first, label it first. What's the name of this junction? J15. So I want to design for example, at J15, a demand of 1000 gallon per minute. In the per demand, basically demand increases. So, so it will show you the mark here that for this alternatives, all the demands, all the junctions are same. It is the best demand, but for this alternative, only the demand changes for J15. So for that, I will create another scenario here. From here I will create a new scenario. Oh, create a new child scenario, and fire demand. I will give a fire flow, and for this scenario I will go to the demand and will change the alternative. So what's are the, so this is basically the alternative which we have defined. So I will make it current. Okay, and we'll run the simulation. So you can observe that the demand at this junction increases very high. So therefore it give us the negative pressure. And okay, to supply a water to these junctions, I will just make it the dia of. Let me increase the die of pipes in order to accommodate these demands. I want to make it. बस दर्जी एकदम ستړی شوم کنه یار
صحیح دی
بس دا یو انالیسس درته کوم بس بیا کلاس وایند اپ کو. So I change the dia of each pipes. Hydraulic equations, why not? So it is solving. I think we have given I think the tank has and such that capacity in order to fulfill the demand. So I will increase the elevation, base elevation. I will make it to be 7, 10, 50. Engine calculation failed. To obtain completely the problem, choose analysis and validate. So the node is not connected or isolated from a brand. So these are the difference. It's good that we are getting such type of errors. So we get to know that how to solve this. So these are the different notification you can get, and it is very important to know about these type of problems. So I didn't face these type of problem in my situation. So it's showing, it is telling us that the pipe is not connected to the connected or to or isolated from a boundary or reservoir or tank. So we will check this, that the wear this type of thing. Okay, we have removed the PRV, so therefore it has removed the pipe as well with the PRV. Therefore, it is giving us a error. So it is good that we are getting errors, then get to know that how to solve these type of problems when you are modeling or you are designing a water supply network. Now it will be run, inshallah. Okay, so by increasing the pipe size and the capacity of a tank, you can see that we are getting good results. So based on this, by trial and error methods, you will increasing the size and the die of pipe and the tank, the capacity of a tank, and with different type of mayos you will provide it in order to get the economical and best design. So that's it for today. If you have any questions, we have 2 minutes to wind up because the session is going to over. So if you have any questions, please ask. And if you want to ask in later on, then you can may ask as well as.
Can we convert this diagram into 3D model, sir?
No, the WaterGem hasn't had capability to convert into 3D model.
Okay.
Oh, okay. One thing you can do that. Like for example, if you want to create a graph, you can check, for example, hydraulic grade, or you can also check the elevations of that. And for example, I want to check or for this pipe, I want to check the hydraulic grade for these 3 pipes. Not getting the graph, the hydraulic grade. The owner, I think. Is basically we are doing a for hours. I don't know why it's not showing.